Today I'm going to talk about the different types of bonds that atoms can form. There are two main types of bonding: the very temporary secondary bonds and the much stronger primary bonds. Primary bonds are split up into ionic, covalent, and metallic bonds. I will discuss all of these, but I'm going to start with ionic bonds. These are bonds where one of the elements steals an electron from the other element. This causes the electron stealer, hereafter referred to as the anion, to be negatively charged, while the electron donor, called the cation, has a positive charge. As such, these atoms are now attracted to each other due to the electromagnetic force. The donation and absorption of electrons is based on valence electrons. Valence electrons being electrons in the outermost shell of an atom. The specifics of what an atomic shell is aren't important. Just be aware that atoms like their outermost shells to be full of electrons. Atoms to the far left of the periodic table, alkali and alkaline earth metals, typically have just one or two electrons in their outer shells, so it is easiest for these atoms to obtain a full valence shell by losing these electrons. In a similar vein, atoms to the far right of the periodic table, aside from the farthest right column, which already has a full outer shell, are missing a couple of electrons from their valence shell. As such, it is easier for these elements to absorb electrons to fill their outer shell. What you can derive from all of this is that metals on the left end of the periodic table lose electrons to form cations, while nonmetals on the right of the table gain electrons to form the anion in ionic bonds. Now we move to covalent bonds, where the electrons are shared rather than donated. In this case, atoms needing extra electrons, i.e. nonmetals, share the electrons they do have with other nonmetals, effectively filling up both of their valence shells by sharing. Since this bond is based on the sharing of electrons between two specific atoms, covalent bonds are directional. This means that the bond only takes place between the two involved atoms. This is opposed to the non-directional ionic bonds, where any charged atoms, or ions, will be attracted to any oppositely charged ion. This is because the electromagnetic force acts equally in all directions for these ions. No one charged atom is preferred. In addition, covalent bonds are generally a bit weaker than ionic bonds, but it really depends on the elements involved. Interestingly, there is no fine line between ionic and covalent bonds. Rather, they form a spectrum of electron stealing versus sharing. Where a particular atomic bond falls on this ionic covalent spectrum depends on the electronegativities of the two elements. Electronegativity is a measure of how much an atom wants to hold on to its electrons. So, the alkali and alkaline earth metals, which, as I mentioned earlier, want to lose electrons, have low electronegativities. The nonmetals, then, have comparatively high electronegativities, because they would rather gain electrons than lose them. The difference in electronegativities between the two elements, then, determines how much the electrons are shared or stolen. The larger the difference in electronegativities, the more the electrons are stolen, and thus the more ionic the bond. Likewise, the smaller the electronegativity difference, the more the electrons are shared, and thus the bond is more covalent. At intermediate electronegativity differences, we have what is known as a polar covalent bond. In this case, electrons are still shared between the two elements, but they tend to spend more time around the more electronegative atom. There is actually an equation that can determine the percentage of covalency against percentage ionic. This is percent covalency equals 100% times e to the x sub a minus x sub b divided by -4, where x sub a and x sub b are the electronegativities of the two elements in the bond. Metallic bonds, however, are quite a bit different. Since metals have low electronegativities, they tend to lose electrons. As such, when metal atoms come together, electrons don't stick to one atom, but tend to float around between atoms. This is often described as a sea of electrons, where electrons just float around on the sheet of metal. Thus, in a sense, metallic bonding is kind of like a widespread covalent bond. However, for the most part, metallic bonds do not have ionic tendencies. The electrons are usually just shared. Also, except for a few specific metals, metallic bonds are weaker than both ionic and covalent bonds. Furthermore, note that for covalent bonds, the bonding took place between two specific atoms, whereas metallic bonding can theoretically have an infinite number of atoms involved, similar to ionic bonds. This feature is actually part of what makes metal so good at conducting electricity. Electrons can easily flow along the entire length of a metal wire because it is all effectively part of one bond. Now we move on to secondary bonds, also called van der Waals bonds. Starting with the weakest of these, we have the instantaneous induced dipole bond. While any normal atom is electrically neutral, the charge isn't always evenly distributed. There is a chance that the electrons surrounding an atom happen to be more heavily concentrated around one side of that atom. When this occurs, there is now a charge distribution, with the electron-heavy end being slightly negative, and the other end being slightly positive. This slight charge concentration is called a dipole, and it is actually strong enough to disturb the charge distribution in other nearby atoms, i.e. create other dipoles. Let's say, for example, that the slightly positive end of the randomly formed dipole is the closer end to another atom. Since the positive charge of the dipole is closer to the other atom, it is stronger than the slightly farther away negative charge at the other end of this randomly formed dipole. This means that the electrons in the other atom are attracted to the dipole, which further means that the electrons in the other atom are now unevenly distributed, i.e. another dipole is formed. Since the randomly formed dipole has its positive end near the created, or induced, dipole's negative end, there is now an electromagnetic attraction between these two atoms. Note that this basic process still applies if the negative end of the random dipole is near the other atom. We have a sign change on the charged ends for both dipoles, but they are still attracted to each other. As you might expect, these instantaneously induced dipole bonds are extremely weak, and will quickly be overpowered by any of the other bonds. Nevertheless, this force still exists. A slightly stronger secondary bond is the polar-induced dipole bond. In this case, instead of polarization randomly appearing due to an uneven charge distribution, one of the molecules is already polarized. This permanent polarization results from the polar covalent bond that I mentioned earlier. This polar molecule still bonds to another atom or molecule using the same process as that of the instantaneous induced dipole. The slight charge distribution in the polar molecule causes a similar charge distribution in another atom or molecule. This induced dipole then bonds to the polar molecule by the same electromagnetic force. Note that, while still weak, this bond is stronger than the instantaneous induced dipole bond, because a dipole already exists. One does not have to randomly form. Also note that all of these secondary bonds are directional, despite being based on the electromagnetic force. This is because, compared to ionic bonds, the electromagnetic force for these secondary bonds is quite weak, and thus cannot really extend beyond the two involved atoms. The last type of secondary bond we have is the permanent dipole bond. This occurs between two permanent dipoles, such as those formed by a polar covalent bond. This bond is stronger than both instantaneous induced dipole bonds and polar induced dipole bonds because there are no induced dipoles. Rather, the positive end of one of the permanent dipoles aligns with the negative end of another permanent dipole and forms a bond due to the electromagnetic force. There is a specific high-strength form of this bond known as the hydrogen bond. In this case, the bond specifically takes place between a positive hydrogen and one of the very electronegative atoms, fluorine, oxygen, or nitrogen. The bond is still permanent dipole in form, but is much stronger because the charges on both the hydrogen and the other atom are greater than for normal polar molecules. This increased charge magnitude means that the electromagnetic force is stronger. Note that while these hydrogen bonds take place between different molecules, the dipole will only form when the hydrogen and either fluorine, oxygen, or nitrogen are covalently, or more accurately, polar covalently, bonded. Water is a good example of a molecule that forms hydrogen bonds. Nevertheless, hope you enjoyed it, hope you learned something, and see ya!